Hello everyone, myself N.Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the previous session, we have seen the strain energy subjected to bending and twisting. Now along with that, we have seen potential energy of the transverse load. Now here in this module, we are going to see the potential energy of the in-plane loads. Okay, so the potential of the in-plane loads. So as we have discussed in the previous sessions, in-plane loads are nothing but the additional loads which can be encountered on the aircraft surface in addition to the bending, shear and torsional loads. And to understand the effect of these in-plane loads to calculate the potential energy, and we'll just try to understand this diagram. So we'll take one elemental strip of width delta y, and this is the delta y, and other length you can consider as delta x of the plate which is shown in figure. Then let us consider the plate dimensions also as A cross B, and on this let's try to incorporate the in-plane loads which are in-plane compressive loads, that is Nx and Ny are the in-plane compressive loads which you can see here and which are acting on the two edges of the plate. Nx compressive load, and on the other two edges you can see Ny is a compressive load acting on this edge, and opposite to it also it is again taken as Ny compressive load. And apart from these direct loads, we have the shear loads also, and the shear loads you can see here clearly it is taken as Nxy and Nxy on this one because it is equal and opposite. So and again it acts on the four edges of the plate. So these are the Nx, Ny and Nxy, the in-plane loads which are acting on the plate element. Now what we do here it is we'll take an example of only first one load so that we can write with the other load effects also. So let's try to understand with Nx load first. So Nx is the compressive load. To understand this, let's try to take the compressive load on the strip Nx, and Nx is acting on the delta y edge, and the total force is nothing but you can write it as Nx into delta y. So it is a compressive load on this strip is given by Nx into delta y, and due to bending of the plate, the horizontal length of the strip decreases, and let us assume that it decreases by an amount lambda. So when the Nx delta y compressive load is acting on the two edges, so let us assume the length is reduced by an amount lambda. Okay, so now we have to calculate the lambda. So what is this actual length? Because we considered the plate length as A, and reduced, we are saying that it is reduced by an amount lambda, and remaining amount we are taking it as the A dash is the remaining length, and A is the actual length which is taken for this curvature. Okay, and for this, so we have to find an expression for lambda. What is that reduced length? So to get that, let's try to assume that we'll try to consider one small element, and let us assume again for this small element, and on the left side let us assume the deflection is W, on the right side let us assume the deflection as W plus delta W, and let us assume also the edge length what we considered is delta A. Okay, the small elemental strip what we are considering in this. So with these notations what we have given here, let's try to follow this one. So from the diagram, the potential energy delta Vx corresponding to the load Nx into delta y, and which is referred to the undeflected position of the plate, and it can be written as delta Vx as minus Nx into lambda into delta y, where Nx into delta y is the load and lambda is the displacement. Okay, so now here delta Vx equals to minus Nx into delta into minus Nx into lambda into delta y. So from the figure you can write for a small element delta A of the strip in which dou W by dou X is small. So you can write for this small element, you can consider this as a small element. So this is the element what we have, and you can consider it as approximated to triangular element, and in which you have this is delta A, and you can see here this is W and this is dou W plus delta W, so that you can write this as delta W, and this length you can consider as delta X. So from the Pythagoras theorem you can write this as delta A square equals to delta X square plus delta W square. Okay, from the Pythagoras theorem, you can write it as delta A square, that is equals to delta x square plus delta w square. So from this we are going to write the expression from here. So delta A can be written as under root, that is 1 by 2, delta x square plus delta w square all to the power of 1 by 2. If you try to expand this like a mathematical expansion, so you can write it as delta A, that is approximately equals to, when you take delta x common from this one, so you are going to get delta x of 1 plus delta w square by delta x square whole to the power of 1 by 2. This is just like 1 plus x square whole to the power of 1 by 2 or 1 plus x whole to the power of 1 by 2. So you can take any of the expansion, mathematical expansion, and then you can write it as delta A equals to delta x of 1 plus half into dou w by dou x whole square. So this you can write it as what? 1 plus half into dou w by dou x whole square. Now delta A, now when you try to write this equation, delta A can be written as A for the complete plate, and on the right side also you can integrate it from 0 to A dash, and therefore you are going to get A equals to integral 0 to A dash 1 plus half into dou w by dou x whole square into dx. And further you can integrate this one, integrates to x, and when you try to substitute its limit, you are going to get A dash plus the second term you can write integral 0 to A dash half into dou w by dou x whole square into dx. So half into dou w by dou x square into dx, and then you can take this A dash to the left side, A minus A dash you can write, and from the diagram you can clearly see this is A and this is, you are subtracting A dash, so it's going to give lambda. So from the equation here, A minus A dash, that is equal to lambda, which is equals to integral 0 to A dash half into dou w by dou x whole square into dx. Now this integral 0 to A dash, which is nothing but half into dou w by dou x whole square into dx, it only differs from integral 0 to A half into dou w by dou x whole square into dx. So A dash is again very small length, so you can approximate it to A, so that by a term of negligible order we can write lambda as equal to integral 0 to A 1 by 2 dou w by dou x whole square into dx. So this is the reduced whenever the nx into delta y compressive load is acting on the edge of the plate, so therefore it reduces by an amount lambda. Now that amount is given by lambda equals to integral 0 to A half into dou w by dou x whole square into delta x. Now if you try to remember the potential energy Vx of the applied loading, so Vx, that is equals to, we have written already the formula here, that is Vx minus nxy into lambda into delta y. Now in this lambda we are going to replace it. Okay, so in the place of lambda whatever we have got, that we are going to replace it. This is for the very small element, and we are going to write for the complete plate of A cross B. When you try to write that, you are going to get Vx, that is equals to minus half. Earlier what we have, delta Vx equals to minus nx into delta y into lambda. Okay, so here when you try to write this equation, Vx, that is equals to minus half integral 0 to A integral 0 to B, that we use double integration because you are going to consider the plate 0 to A 0 to B, and nx is as usual and delta x is as usual, and you are going to write dou w by dou x whole square into dy from the previous expression. So from this is the Vx contribution. Now the potential energy of the in-plane load, that is nx loading, when you try to write Vy, then you are going to write Vy equals to minus half integral 0 to A integral 0 to B ny into dou w by dou y whole square into dx dy. So these are the two contributions of the potential energy due to nx load, which and ny load also we have written. This is nx load contribution for the potential energy of the in-plane loads, and this is ny load contribution. So in a similar manner you have to see the nxy contribution also, that you can see here in the next slide. And to understand that, we are considering this diagram, and in which you will consider the two slopes. One slope is dou w by dou x and the other slope is dou w by dou y. Okay, so already you have written two contributions. In the similar manner you can write the contribution of nxy also, because here we have dou w by dou x whole square, here we have dou w by dou y whole square. Next, when you write the contribution, you can write the contribution of that as nxy into dou w by dou x is one slope and dou w by dou y is the other slope. So that you can write. So with this you can write the contribution as half into nxy into delta x, that is acting on the delta x edge, and dou w by dou x into dou w by dou y. Similarly, when you try to write on the delta y edge, the nxy contribution, you can write it as half into nxy into delta y into dou w by dou x plus, sorry, dou w by dou x into dou w by dou y. When you try to combine these two contributions on delta x and delta y edges, you can write this as half into integral 0 to a integral 0 to b 2 nxy dou w by dou x dou w by dou y into delta x delta y. So this is the contribution due to nxy, the shear loads. So earlier we have seen the nx contribution and we have seen ny contribution. Now we have seen the nxy contribution. Let us try to write this as equation number 3, and let us try to write this as equation number 1 and this as equation number 2. And when you try to add these three equations, you will get the total contribution of nx, ny and nxy loads. So the total contribution of nx and nxy loads can be written by using these three equations, and it is written as vxy, that is equals to minus half, sorry, so this is another contribution nxy. So when you try to add all these loads, you can write the total potential energy due to the in-plane loads is given by minus half integral 0 to a integral 0 to b nx into dou w by dou x whole square plus ny into dou w by dou y whole square plus 2 nxy into dou w by dou x into delta x delta y. So this is the potential energy of the in-plane load. So to solve any particular problem, and if you want to find out the deflection shape of the plate, then the total strain energy must be added to V. So the total potential energy pi is the summation of strain energy subjected to bending and twisting plus potential energy of the applied loading. So if the load is given transverse load, we are going to use it as the transverse load potential energy, will write it as a transverse load expression. And when the in-plane loads are given, the previous equation is going to be used for the potential energy. So first you have to write the expression for strain energy, next you have to write the expression for potential energy. Those two you have to add, and then you are going to get the total potential energy. So for example, earlier we have seen the strain energy expression, that is integral 0 to a integral 0 to b into d by 2 of dou square w by dou x square plus dou square w by dou x dou y square whole square minus 2 into 1 minus nu dou square w by dou x square into dou square w by dou y square minus dou square w by dou x dou y whole square. And for this is from here to here, up to here it is u, and for which you have to add v. If you try to take transverse load, so the transverse load is nothing but w into q naught into delta x delta y. That if you try to take to the add to the strain energy, you can take minus w q naught into dx dy. So this is u plus v, total potential energy. So now the total potential energy, when you add and then you integrate, and in which w is a deflection, you can assume that as amn sin m pi x by a sin n pi y by b. So all this term, so this term w has to be differentiated twice with respect to x and substitute here, and this term w is to be differentiated with respect to y and substitute here twice, and here again 2 times differentiation with respect to x, 2 times differentiation with respect to y, and here 1 time differentiation with respect to x and the next differentiation with respect to y, and q naught also you can assume in the form of a small amn sin m pi x by a sin n pi y by b. All these should be differentiated separately and substitute in this equation, and when you do that, you are going to get this u plus v, that is equal to integral 0 to a integral 0 to b d by 2 summation m equals to 1 to infinity summation n equals to 1 to infinity a square mn pi power 4 m square by a square plus n square by b square whole square into sin square m pi x by a into sin square n pi y by b minus 2 into 1 minus nu m square n square pi power 4 by a square b square into sin square m pi x by a sin square n pi y by b minus cos square m pi x by a cos square n pi y by b minus q naught into, again for w you can substitute summation m equals to 1 to infinity summation n equals to 1 to infinity amn sin m pi x by a sin n pi y by b into dx dy, out of which the complete equation, if you try to look at this 2 into 1 minus nu containing term, when you try to integrate this, you are going to get a by 2, b by 2. When you try to integrate this cos square, you are going to get a by 2 and b by 2. So ab by 4 minus ab by 4, it gets cancelled upon integration. So therefore, the 2 into 1 minus nu containing term straight away integrates to 0, and we try to write the rest of the equation as u plus v equals to d by 2 summation m equals to 135 to infinity summation n equal to 135 to infinity a square mn pi power 4 ab by 4 into m square by m square by a square plus n square by b square whole square minus q naught into summation m equal to 135 to infinity n equals to 135 to infinity amn 4 ab divided by pi square mn. So here the odd values are taken, because when you take again even terms, again this integrates to 0. So therefore we have taken odd values. So finally, from the principle of the stationary value of the total potential energy, we have to make this equation u plus v equal to 0. The total potential energy must be minimum. So for minimum or maximum, we have to substitute the total potential energy, that pi equals to u plus v should be equal to 0. And this complete equation is made equal to 0. That is differentiation. Dou of u plus v by dou amn. The complete equation should be differentiated with respect to amn, and the derivative must be set equal to 0. And this has been done here. And after substituting the derivation, after doing the derivation, and when you make it equal to 0, we'll try to write amn from this. So from this complete equation, amn can be written as 16 q naught divided by pi power 6 d into mn m square by a square plus n square by b square l square. This is the amn unknown coefficient which we have to find for any problem. Once you get this, you can substitute for w, that we assume summation amn sin m pi x by a sin n pi y by b. So in place of amn, you can substitute this unknown coefficient, and this gives the total deflected form of the plate using energy method, that is w equals to 16 q naught by pi power 6 d summation m equal to 135 to infinity summation n equals to 135 to infinity sin m pi x by a sin n pi y by b mn into m square by a square plus n square by b square whole square. So this is the way we find the deflected form of the plate using strain energy method, that is strain energy subjected to bending and twisting plus potential energy of the applied load, which in turn called is a total potential energy, that is the strain energy method. So this is the strain energy method which we have seen. Okay, so thank you for everyone watching this one. So in the next module, we are going to see unit 2. Thank you.